Okay, we're going to get started. So there is a handout down at the front if you'd like to grab a paper copy of the handout. There's also an electronic copy online if you look at the page that says tutorial November 26th. We're going to get started, all right? So let's start to quiet down, please. So you can find the handout at the front. You can also find it on Quarkus if you'd rather follow along on your tablet or whatever device. And yeah, we'll get started on some dynamic force analysis today. But before we do, I'm going to take a look at some of the problem set problems because there are some common questions that are coming up. So I thought that we could discuss those really briefly because I'm sure many of you will have those questions as well. So one of the questions on the problem set is what direction is the force on the workpiece applied? And just assume that it's vertical. So it's just straight up and down. Okay, it's just perpendicular to the ground. So that should be pretty straightforward there. So that was one question that was coming up. Another question that was coming up is what is the direction of the force on this slider? So like we talked about in our last tutorial, when we draw sliders like this, it's usually just a shorthand because we don't want to have too much cluttering the page, but there's actually two walls that constrain it in either direction. Okay, one on either side. So this slider is free to move in the vertical direction, but there's some force with a line of action that's perpendicular like this that constrains it in place. And that force could either be to the left or right. Okay, that's another question I was getting. Another question is, what's the deal with this cylinder? You know, we're given a pressure in the cylinder and we're given a diameter, so we can calculate the force that's in the cylinder itself. What does that mean for the rest of the mechanism? Well, you can think about that as a force applied here on the inside of the cylinder that's pushing this part out and this part this way. So the force in the cylinder is really just the force that it applies. In this case, I'm drawing it with positive pressure. It's the force that it applies to its surroundings. So the force in the cylinder is equivalent to saying the force that this link is carrying. Another way we could have done this is we could have just drawn a regular link and we could have told you that the stress in the link was 100 kilopascals and the diameter of the link was 1 centimeter. So it's just a way of telling you what the force is in that link. So don't get tripped up by the cylinders. Any questions about that? Oh, yes?
Do we have to worry about the mass of the slider?
You're not given the mass of the slider, so no. There's no way to account for it because it's not given in the problem. But if this were, a design project, then yes, you would have to consider what is the mass of the slider. You'd have to consider the mass of all of these links and think, is that going to be a significant force in this problem? But in this case, you're not given that information, so there's no way to account for it. So you don't have to account for that. Okay, this problem is the number one problem that I'm getting questions about. And so the recommendation here is to use the superposition principle because there's two forces. There's a weight force here. That's M3G. And then there's an applied force P over here. So with superposition, we can consider them one at a time. So for the first part, you might get rid of this force and only consider the string here. And then for the second part, you might get rid of this force and only consider the weight. When you do that, a lot of people are pointing out that this becomes a 4-force link because there's 1, 2, 3 connections here, pin connections. Each of them have a force. And then there's the weight of the link here. Okay? So that means that these two links here are 2-force links. So I would recommend before you do a complex link like this one that has 4 forces, start from the easy stuff. Look at your 2-force links and start thinking about what they're showing you. So if this is a 2-force link, the line of action of this force is like this. This one's also a 2-force link. It has a line of action like this. But that's a problem, right? Because at this point, this claims to be the line of action of F6 on 5. This one claims to be the line of action of F5 on 6. Those should be equal and opposite. So how can they possibly have two different lines of action? The only possible solution to this problem is that that force there at the connection point is equal to 0. That's the only solution that's valid for two lines of action that are going in different directions for the same force. So the force there is 0, which means the force up here is also 0. The force at the point D. So in that case, you just have a 3-force link. Okay? Any questions about that? Great. So those were some of the questions that I was getting in the office hours this week. All right, let's get started on the main material for today. Unless there are any other questions about the problem set. Yeah. Problem 2 with the cylinder. Yeah, so let me just quickly sketch that on the page here. When you have a cylinder that looks something like this. So given the area and the pressure in the cylinder, we can calculate the force inside the cylinder. And the force is going to be pressing on the inside. It's going to be forcing these two parts of the cylinder away from one another if it's a positive pressure. And that force is going to be transmitted to the other parts of the links. So you can think that there has to be, if this is in static equilibrium, there has to be some forces opposing this internal force here that's driving the link apart. So when we get the force inside the cylinder, that's equivalent to just saying the force that is applied on either end of the connection points here and here. So it's just equivalent. So this is F cylinder. This is, like, let's say this is link, I don't remember what link number it was. Let's say this is link 3, and then maybe there's a link 2 over here and a link 4 over here. So this is F4 on 3. This is F2 on 3. So in that case, they're just going to be equal in magnitude to F cylinder. Yeah, that's all I'm saying there. So it's a way of telling you what the force in that particular link is.
Thank you.
You're welcome. Yes, another question.
You were just saying the positive pressure means that it's just pushing out from each other, and so we know that the forces should be, like, we know the direction of the two other forces.
That's right.
Like, I'm saying we know, like, we can say that we know the direction of F2, 3, and F4.
Sorry, could you quiet down over there? I'm trying to hear this question. Yeah.
I'm saying we know the direction, we can say that we know the direction of F2, 3, and F4 just because of the positive pressure, right?
Yes, that's right. Because if there's positive pressure in here, we need to have opposing forces that keep this link in balance here, in equilibrium. If there was a negative pressure, then that would be like a vacuum inside, and that would be pulling the cylinder inwards. And in that case, we would know that the forces applied to the link on the other side here would have to act in opposition to keep the link in equilibrium. You're welcome. Any other questions about the problem set? Excellent. Okay. So today we are going to be talking about dynamic force analysis, which is something that was covered recently in the lectures. And I'm a little overexposed here. There. Okay. So in the lecture, one method that was discussed was the inertia circle method. And the basic idea is that, like, let's say you have a general body like this, and there's a force applied here, and maybe a force applied here at two different connection points. And let's say that maybe this link that attaches to it is a two-force link, so maybe we know the line of action of that force. So if this is link 3, maybe this is the line of action of F4 on 3. And we have some center of mass over here. And let's call that G3. And our object is accelerating. Its center of mass is accelerating in this direction. Let's call that AG3. And then the link, because it's just a general body, it could also be rotating with some rotational acceleration. So let's say that the angular acceleration is some theta double dot 3, which we know we've done our acceleration analysis, we've done our acceleration polygons, and we've determined these values. So these are both known. They're either known already or given in the problem statement, which is what we'll do today. So we can use D'Alembert's principle, where we replace these accelerations with an equivalent inertial force, which is a fictitious force. So we can create a force called FIN, which is equal to negative m3, the mass of length 3, times the acceleration of its center of mass. And we can define an inertial moment analogously that is equal to the moment of inertia, the negative moment of inertia, times the angular rate of acceleration. Okay, so in that case, when we draw these on our diagram, our inertial force is going to be in the opposite direction to that acceleration. So it'll be pointing this way, like that. And our inertial moment is going to be acting in the opposite direction to theta double dot. So our inertial moment is something like this. Okay, and there's some F23 applied over here that we don't know. So for a dynamic force analysis problem, let's say we're trying to find F23. And we'll notice that in this problem we have an applied force here, we have an applied force here, we have an applied force here, and then we have a moment. So we're almost a three-force link, but because of this moment, we can't use our standard three-force link graphical solution methods. So one thing that we could use to solve this problem is we could do sum of moments and sum of forces analytically and solve the problem that way. That's a perfectly valid solution. Or we can use a method called the inertia circle method. And with the inertia circle, what we're going to do is we're going to move the application point of the inertial force. So it's going to stay pointing in the same direction, but we're just going to shift it either this way or this way in order to induce an equivalent moment to the inertial moment about this point, about the center of mass. So if we're going to do that, we want to offset that force in the perpendicular direction. So we can take a perpendicular line. Well, actually, we'll do it slightly differently from how Professor Diller does it in the lecture. So with the inertia circle, it's going to have some radius. We usually call it rho. And the couple induced by our inertial moment is going to be the inertial force times rho. So this is just a moment. FIN times some distance is going to be equal to MIN. Because we want our FIN to be shifted by some distance rho that creates the same amount of moment as our inertial moment. So we can solve for the magnitude of rho. It's just going to be the magnitude of the inertial moment divided by the magnitude of our inertial force. And remember that if we know our accelerations, we're given our masses in the problem, so we know our inertial force and our inertial moment. So we can plug them in here, solve for rho, and we'll get some value of rho. And we're going to do that today, but I'm just going over it a little conceptually at the moment. Once we have that value for rho, you could draw a perpendicular line and offset that way. Or you could take your compass and you could set it to whatever that distance is. So let's say that rho was like, 2.1 centimeters, 2.2 centimeters. Then I would have set that distance on here. And we could draw out a circle. There. And that's our inertia circle. And it has a radius of rho. And then we're going to offset our force so that it's tangential to that circle. So I'm going to take my drawing triangles, I'm going to line it up with the inertial force there, and I'm just going to shift its line of action over until it's tangential with the edge of that circle, like that. Now the question is, if our inertial force is pointing up and to the right, and our inertial moment about our center of mass is clockwise, what direction, what side of the inertia circle should we be putting our force? Should we put it on the bottom right side or the top left side to get this equivalent moment? I heard a top left. It was a little mumbled, but I heard it. Yeah, that's right. Because we want to create a clockwise moment. So with this force, put it up on this side, we're going to get a clockwise moment using the right-hand rule. Okay, so we shift our force up in this direction. So now this is equivalent to saying that we have that inertial force applied up here. And now we can ignore the moment because we've accounted for it by offsetting our inertial force. And now we just have three forces. We have F4-3, we have FIN, and we have F2-3. So we can solve our problem like we would normally for a three-force link. So the whole point of this method is simply to come up with a way for us to do these dynamic force analysis problems the same way that we do our static force analysis problems. So there I could identify the K point, and then I know that the line of action of F2-3 passes through that point, and then I can construct my force polygon and move through the rest of the solution as we would for any other static force analysis problem. So that's the idea there. And we're going to actually do that with a real example here. There's handouts at the front, or you can find them online on Quarkus. Any questions before we move on to a real example? Yeah.
Yeah, so like you have like M there, right? So like you calculate FIN with M. So like how come there's no force of gravity on your link?
Yeah, good question. So the question was, why is there no force of gravity included in this problem? Because we have some non-negligible mass M3. So there's two possible explanations for that. One possible explanation is that the acceleration A is significantly higher than 9.81 meters per second squared. So if it was like 981 meters per second squared, it'd be 10 times larger than the gravitational force. So maybe the gravitational force is negligible in this problem. That's one possible explanation. That would be a very fast acceleration though, 10 Gs. So that's unlikely. The more likely explanation would be that this link is moving in the horizontal plane, in which case gravity is into the page, and it doesn't affect our motion analysis. So that would be the other case where we don't need to include gravity. Does that answer your question?
Like would it be stated in the question if like gravity is negligible or like horizontal plane?
Yeah, usually we would tell you in the problem statement, it would either say something like the mechanism acts in the horizontal plane, or it would just say gravitational forces are negligible. That is correct, yeah. Yeah, you're welcome. Any other questions? Yes?
Sorry, could you just repeat how you chose the point for the new FIN?
Yeah, so I want to place my inertial force. I'm trying to offset it from the center of mass, and I want to offset it in such a way that it causes this moment, MIN, about the center of mass. So MIN was a clockwise moment, so I want to place my force so that it's causing a clockwise moment, which in this case is to shift it up this way. If I shifted it down this way, then our inertial force would be pointing, I'm going to use a different color here, in this direction. And that is going to be causing a counterclockwise moment about G3, which is the opposite of what we want. We want to be simulating this inertial moment. So that's going to be wrong. That's in the wrong direction. Does that answer your question? Yeah. Okay, great. Thanks. Yes, another question.
When you were answering the previous question, you mentioned about like moving the force to create the moment MIN, but you crossed MIN out, so that's why I got a little bit confused for a second. Like, should we have crossed out FIN and then we moved over there and then that causes?
Yeah, actually, you're right. So the question was, shouldn't we have crossed out FIN and not just MIN. Yeah, that's right. So this force, we've actually moved it. It's over here now. And this MIN is gone. So we could have redrawn. So our original free body diagram was something like, I'm just going to re-sketch it. Something like this. Here's our G3. And we had FIN and MIN. And we're going to make an equivalent free body diagram that is like this. There's also these other forces applied here. There's an F4,3 and an F2,3, and they're off in some direction. And so we're going to draw an equivalent free body diagram. Here's F2,3, here's F4,3. Here's the center of mass. And we've shifted that FIN over to here, like that, by some distance rho, some perpendicular distance rho. And these two free body diagrams are equivalent. So that's the idea of what we've just done here. It's a little messy because I redrew over the same diagram, but that's generally how it'll look when you're solving these problems. But this is the idea, that we've gone from having a force and a moment, and we've moved the force over to account for the moment so that we don't have to include it. We can just consider 3 forces, and now this is a 3-force link. And we can solve it that way with our graphical analysis. Does that answer your question?
Yeah, thank you.
You're welcome. Any other questions before we move on? Excellent. Hopefully, if you do have any more confusions, it'll become clearer as we do a real example. Okay. I realize I need some of these as well. There's 2 left, which is exactly how many I need. Okay. We are given this problem, which is actually just taken straight out of the textbook. So I'm going to give some of the missing givens here. So we're given the mass of link 3, which is 3 pounds mass. We're going to be working in imperial units today, my favorite. Sorry, was there a question? Was that a question or no? Okay. And here we have 47.0 pound mass inch squared. And the distance from O2 to B is 3.5 inches. The distance from B to D is 9 inches. And yeah, I think that's it. Okay. And so what we're asked to find for this particular problem, let me zoom out a little because I'm losing the rest of the page there. We are asked to find, first, we're just going to find F2,3. So the force on the force of link 2 on link 3, without accounting for rotational inertia. So we're just going to be dealing with the linear inertia of link 3. And then for part B, we're going to find F2,3 with both rotational and translational inertia. And we're going to use superposition. And then finally, part C, we're going to do the same thing, finding F23 using the inertia circle method. And my hope is to convince you that the inertia circle method is the superior and faster method, even if it is a bit more conceptual in nature than something like superposition. Okay. So that's the problem's statement. And we're going to move ahead first with part A. So here's our solution. Part A. We know the acceleration of the link. So the first thing we're going to want to do is find the magnitude of our inertial force, which is going to be equal to m3 times ag3. And because we're dealing with imperial units and we're going from a mass to a force, that's actually, in this case, we have to include the gravitational constant, which is a real pain in the butt. But that's how imperial units work. So we have 3 pounds mass divided by, and I've already converted some of the units here to make it easier for us, 386 pound mass inch per pound force seconds squared. That is the gravitational constant using inches instead of feet. It just makes things a little easier for us here. And that is multiplied by the acceleration, which is given here as 6,350 inches per second squared. 6,350 inch per second squared. And when we plug in those numbers, we get 49.4 pounds of force. So let's say approximately 50 pounds of force. And what is going to be the direction of that force? Well, our inertial force, FIN, as a vector, is going to be equal to negative m times ag3. So it's going to be up and to the right. And we're just going to draw it on page here. Something like that. There's our inertial force. So we're doing part A, so we're ignoring the rotational inertia in this particular instance. It's going to simplify the problem a little bit for us. Okay, so now we know the forces that are applied to the system, and now we can start. So we've represented our dynamics as this fictitious inertial force, and now we can start solving the problem as if it were a static force analysis problem. It just is a mechanism with some links on it, and they're in equilibrium. A mechanism with some forces on it, and they're in equilibrium. Okay, so my usual recommendation is to start identifying which links are special. So for example, there's an input here. It's not included in the diagram, but there's an input M2. It's not going to be very important for us, but there's an input there. Okay, so link 2. Link 2 is not a special link, so we're going to have to use sum of forces and sum of moments to solve if we want to solve for something like M2. Link 3, in this case, because we've written this as the inertial force, it's a 3-force link. And link 4, which is the slider, has only 2 forces on it, the force from the sliding point on the ground and the force from link 3, so that's a 2-force link. And that's all the links in the system, because this is a relatively simple system. Okay, so I like to start by drawing in the lines of action of my 2-force links. And that's going to be perpendicular to the ground here, so I'm going to take that line off. Like this. There. And this is the This is the line of action of F14, F41, F34, and F43, because link 4 is a two-force link. So all those forces share a line of action. Okay, that's all the two-force links we have. Now let's start looking at our three-force links. So we know the line of action of this force. We know the line of action, the direction, and the magnitude of this force. So we can use that to find our point K. There's our K3. And then we know that the force here at the point B, so the force of 2 on 3, its line of action has to pass through that point. And we get a line like that. So this here, this is the line of action of the inertial force. And this one here, oh, you can't quite see that, can you? And this one is the line of action of F32 and F23. Any questions so far? Yes?
How come the line of action of F32 and F23 is along link 3? Oh, I guess because it's a 3 first. I'm kind of confused with the line of action about how we do it with like relatively straight across.
Yeah, so we knew the line of action of of F23 and F32 because there are 3 forces applied to link 3. So if we draw our free body diagram for link 3, it looks something like this. You can't see that? It looks something like this. So we don't know what direction it is, so it's either up or down. This is our F4 on 3. We know the direction and magnitude of our FIN. And so all that's missing is our F2 on 3 over here. So this is a 3-force link. So as we've done in the past for our static force analysis problems, we can find some intersection point K of their lines of action. That's this point here. And we know that all 3 forces have to have their lines of action passing through that point. So that's how we found the line of action of F23. Does that answer your question? Yeah, you're welcome. Was there another question over here? Okay. Any other questions? Okay. So we've found our lines of action, and now we can construct our force polygon. And let me zoom out a little bit for this because it's going to use most of the page. So I like to start with the force, the line of action of the force that I know. We'll do like this. So the known force is the inertial force. I'm going to bring that down. Like that. We're going to draw in the line of action. And now we're going to measure out some scale. So we said that the inertial force was 50 pounds force. So I'm just going to use a simple scale of 1 centimeter for every 10 newtons. So I'm going to measure out 5 centimeters, like that. And that force is up and to the right. This is our FIN. And that's 5.0 centimeters or 50 newtons. So our scale is 1 centimeter equals 10 newtons. All right. And now we can bring down our other forces, lines of action. So our force F43 is a vertical force. So I'm going to use the right triangle to bring that down. like that. And then it actually looks like this other force is approximately horizontal. In fact, it's almost perfectly horizontal. So that's kind of helpful. So I'm just going to use my right triangle to take that measurement off here. We can just slide that down. I'm running out of space here. Slide down like that. Draw in our other line of action. And there we have it. So this force here, the vertical one, this was our F4 on 3. This one here is our F2 on 3. And they have to go head to tail, head to tail, head to tail, because it's vector addition. This force polygon represents the equation Fin plus F43 plus F23 is equal to 0. Okay, so the problem was asking for F23. We can measure it here. We get about 4.2 centimeters, which gives us 42 newtons. So magnitude of F23 is 42 newtons. And it is pointing to the right. So we could say that it's negative 42 newtons in the I-hat direction, or however you want to specify the direction of the force. Yeah, question?
Did you switch to newtons or?
Oh, yeah, sorry, pounds force. Thank you. Pounds force. That's horrible. Okay, pounds force. Yes, good catch, thank you. Too used to working in SI units. Yes, another question. Right, okay, yeah, so the question is, why, so it's understandable why F14 and F41 are vertical, but it's a little difficult to see how F34 and F43 are also vertical like that. And so the reason is that if we draw our free body diagram, this is a free body diagram of link 4. And here we have F1 on 4. And here is the connection point. And so we know that there's only two forces acting on this. There's F14 and there's F34. We don't currently know the direction of F34, but we do know that this is a two-force link. So the forces must be equal, opposite, and collinear. The line of action of this one is vertical. And really, we don't know, it could be up or down, because we haven't solved for this force. But we do know that its line of action is vertical. So that means that F34 must also be along that line, vertical. And it could be up or down. We don't know yet until we solve for the rest of that part in the problem. Does that answer your question? You're welcome. Okay, any other questions on that so far? This was part A. Excellent, okay. So, for part B, let me look at the time. Yeah. So for part B, I'm just going to use the same diagram, but I'm going to use a different color to represent the work. So I'm going to use a blue pen for part B. And we're going to zoom in a little bit. So for part B, we're asked to find F23 with both rotational and translational inertia using superposition. We've already solved the first part, F23 with translational inertia, which is linear inertia. So what remains to be found is finding F23 with the rotational inertia. Because we can use superposition, we can consider there's two inputs here. So we have our theta double dot 3 is in the counterclockwise direction, so that means our MIN is in the clockwise direction. It's in the opposite direction. And because there's these two known inputs to the system, we could use superposition as a method to solve for the effect of both. Okay, so in that case, we ignore FIN for this second part of the problem. We're only going to consider the moment, MIN. And we're going to see how that changes the problem. So for part B, link 2 is still, it's not a special link. Sum of forces, sum of moments. Link 3 now has two forces and a moment. So again, it's not a special link either. We're going to have to do sum of forces, sum of moments. Link 4 hasn't changed. It's still a two-force link. That's helpful because that means that this line of action that we drew before is also valid for this part of the problem. So we could re-highlight that in blue, just lightly. That part is also still valid for this part of the problem. Okay, so we're going to have to use sum of forces and sum of moments on link 3. So let's consider the free body diagram. Link 3 looks something like this. We have some MIN, which we're going to calculate in a moment. We have some line of action for F4 on 3. And we don't yet know what the line of action is for F2 on 3. So if we do sum of forces, then we know that, and I'm just going to do the vector sum here. We know that because there are only two forces present, F43 plus F23 is going to be equal to 0. In other words, F23 has to be equal and opposite to F43. Okay, that's a pretty simple result. But what it means, practically speaking, is that it's going to be parallel. It's going to have the same line of action. So F23's line of action is also vertical, like this. Because the sum of forces must be 0. The only way for that to be true is if these forces are parallel. So that helps us because now we can do the sum of moments and we can measure off a distance between the line of action of F23 and some other point, which in this case will be the point D. So if we do the sum of moments about the point D, that's going to be this distance here, which we can call D, and we can measure from the diagram. So it's going to be, let's say, I like to take positive as being counterclockwise. So I would call this negative MIN plus F23 times D. And that's all equal to 0. Okay, so we've thought about how we're going to approach the problem, but we still actually haven't calculated MIN or D yet. So let's figure out those parts. So let's start with MIN, and I'm going to have to use another page here. We'll use this page here. Yeah, that'll work. So actually we'll cover this part up here. So we're given IG3, and we're given theta double dot 3. Oh, yes, there was a question.
I have a question when you are doing the sum of moments. We don't know the actual direction of F23, so how could you determine whether it's counterclockwise or clockwise?
That's right. Yeah, we don't know the direction of F23. So I've assumed a direction. And if our answer comes out negative, that means that I assumed the wrong direction. That's a good question. Yeah, so we don't know the direction of F23 yet, but I've assumed a direction. I've assumed that it is, I guess I've assumed that it's negative, like pointing downwards in this case. So, yeah, because that would give us a positive moment about the point D. So I've assumed that F23 is pointing down, and if that assumption was wrong, then we will find out shortly. Yeah. Yes, another question?
For these calculations, why do we not take weight into account?
Why do we not take weight into account? Is that the question? Yeah, so the reason we don't take weight into account is because, well, in this particular problem, I suppose it wasn't mentioned, but this mechanism, let's say, is in the horizontal plane. It's operating in the horizontal plane, so gravity might be into the page. And in that case, gravity is not going to have an effect on the dynamics of our mechanism. Another possibility is that the accelerations are significantly higher than gravity. That is not true in this case. Well, 6,350 compared to 386. That is pretty high, actually. But that could be another explanation, is that our inertial forces are significantly higher than the gravitational forces. So in that case, we can assume that the gravitational forces are negligible in comparison. That's another possible explanation. But the simpler explanation is to say, let's just say that this is in the horizontal plane.
So in general, we make that assumption or we don't?
Yeah, so in general, especially if you don't see any like vector like this drawn on the page, like that. If you don't see that on the page, then, or if the problem doesn't state like that there's gravity is pointing downwards or any sort of indication of gravity in the problem, then you can assume that it is not relevant to the problem. Yep, great question. I'm just going to scribble that out because there is no gravity in this problem. Okay, any other questions? Okay, what time is it? So we've almost reached the top of the hour, but I'm just going to finish out this one part here. So what we were doing is sum of moments on link 3. We did the sum of moments about this point here, which is the point D. And we determined the line of action of F23 based on our sum of forces. So now we're going to find our MIN, which should be given from the givens in the problem, and D we can measure on our diagram. Okay, so we're going to start with MIN. So actually, I'm just going to write it in up here because we do have a little bit of space. MIN is equal to IG3 times theta double dot 3. Technically, it's negative because it acts in the negative direction. So let's just say that the absolute value like that. Okay. So we're given IG3, but because this problem is given in imperial units, we actually have to divide by the gravitational constant once again. So we get 47.0 pound mass inch squared divided by 386 pound mass inch per pound force second squared. We're running out of room a bit here, and this is all multiplied by 814 radians per second squared. So that gives us the magnitude of our inertial moment being, what did I calculate previously? 99.1 inch pounds of force. So that's the magnitude of our inertial moment. And as I've already said, it acts in the opposite direction to theta double dot 3, so we know that it's acting in the clockwise direction like that. Okay, the other thing that we needed to find to continue with our calculations was the distance between the vertical lines connecting B and D, or the vertical lines passing through B and D. Because we found our line of action of this force is vertical like that. So this is the line of action. You can't see that. Line of action of F23 for part B. And we can measure this distance on the page. This diagram is a scale diagram, but it is not a one-to-one scale. So it's about 72 millimeters. So this is D. It's about 7.2 centimeters on the page. However, the scale on the page is that 8.5 centimeters is equal to 9 inches. That is the scale of this particular mechanism, the way it's drawn. So in that case, our D is equal to 7.62 inches. Okay. So there's our D, there's our MIN. Any questions about how we found those values? Okay, good. So now we can plug those in down here. And we have that F23 is equal to our inertial moment, which gets put over on the other side. So this negative becomes a positive. So we get 99.1 inch-pounds of force divided by 7.62 inches, which gives us approximately 13.0 pounds of force. And it comes out to a positive number, so that means that our guess direction was correct. So I guessed that F23 was down to cause a positive moment, F23D, about the point D, and I defined positive as being in the counterclockwise direction. So our guess was correct. So that means that this is 13 pounds of force in the vertical direction like that. Okay, but we're not quite done our problem because we were supposed to find with superposition. So I'm just going to go to the next page. I'm just going to write B continued. And so with superposition, we know that F23 total is equal to F23 due to the inertial force. I'll just call that F23F plus the force F23 due to the moment, the inertial moment. So that gives us, so F23F we found previously was 42 pounds of force. And it was in, the left direction, like that. So one way we could represent that is negative 42 pounds force in the I hat direction, assuming we define some x and y directions like this, x and y. So that's our I hat, our j hat. But I'll just use a symbol to indicate the direction that it's horizontal and to the left. And we're adding it to 13 pounds of force, which was downwards. So that's equivalent to writing negative 13 pounds of force in the j-hat direction. So this is one way we could represent our final answer. Or we could also say that the magnitude of F23 is equal to just the vector sum. So that's the square root of 42 pounds force squared plus 13 pounds of force squared. So the magnitude of F23 is equal to approximately 44 pounds force. And you can check my math on that. So that's our answer there. Okay, so that was a lot of work to get to that answer using superposition, which was previously the only other method in our toolbox for solving this kind of problem, was to use superposition if we were presented with both a moment and a force. After the break, I will show you the inertia circle method, which will take us probably less than half the time, probably a quarter of the time. So that will show you that it's very helpful, very advantageous, and I would encourage you to use inertia circles for this kind of problem on your exam rather than superposition, because it will save you lots of time. But let's take a break. Let's take 10 minutes, because I don't expect us to take more than 15 minutes after that, and we'll have time afterwards for extra questions, or you can leave early if you wish. So for now, let's take a 10-minute break. We'll reconvene at 11:18. Okay, we're going to get started again. So, if all goes well, I'll have you out of here in 10 minutes, so we can continue our chatting after that. If you have any more questions, you can come down to the front afterwards and ask me. So for part 3, I'm going to continue with a black pen. So for part 3, we're going to use the inertia circle method. Okay, so the first thing that we need to determine, we've already figured out our inertial force and our inertial moment. So we need to find the radius of the inertia circle, rho. That's going to be equal to the magnitude of our moment divided by the magnitude of our inertial force, which is, we had 99.1 inch pounds force divided by 50 pounds force. So thankfully we have common units here of pounds force, so there's no unit conversions involved, thankfully. These just cancel out. And we're left with approximately 2.0 inches. Okay, so as I mentioned before, the scale of this diagram is not quite 1-to-1. We have that 8.5 centimeters is approximately 9 inches. So this is page, and this is actual. That's our scale. So this 2 inches is actually approximately 19 millimeters on the drawing or on the page. Okay. So where did I put my ruler? It's hiding under here. We're going to use the ruler with the compass. This is one way of doing it. It's not the only way. And we're going to get 19 millimeters. It's around there. Something like that. Okay. we're going to draw in our inertia circle. Like that. And it has a radius of rho. And if we remember, our inertial force is in the opposite direction. This is our inertial force. It's in the opposite direction to our acceleration of our center of mass. Again, I'm hiding my triangles underneath my other notes here. Okay. And our inertial moment is in the opposite direction to theta double dot 3. So our inertial moment is this way. That's our MIN. So we need to shift our inertial force so that it provides the same moment, so we can just account for the inertial force and we don't need to account for the inertial moment. So how are we going to do that? Well, if we want a counterclockwise moment about G3, we need to shift FIN up this way. So that's what we're going to do. We're going to take that line of action, shift it up so it's just tangential to the circle. And this is our new line of action here of our inertial force. So this is that inertia circle method. I'm just going to sketch it in a little farther, like that. And this is the line of action of FIN. And I like to write like plus inertia circle to indicate that we've extended FIN to a separate place to account for our MIN. So as a reminder, this is what we've done. We started with something like this, where we had some unknown link forces. We had a known inertial force and a known inertial moment, and we've created an equivalent free body diagram where we still have these unknown forces at the points of connection, but we've shifted FIN over to give us an equivalent moment because FIN causes a moment couple about G. And so these two free body diagrams are equivalent. And now we only have three forces, and it becomes a three-force link. So that's exactly what we've done in this problem. We've shifted our FIN up here, so it's still pointing in this direction. But now we're accounting for the moment MIN. Okay. So we've done the inertia circle. And now let's consider what we know about these links now that we've done that. So once again, let's look at link 2. So as I mentioned, there's an unlabeled point here. There's actually a moment here, M2 on link 2. So link 2 is not a special link. So if we wanted to solve it, we'd have to do sum of forces, sum of moments. Link 3 is a three-force link now. And this is because inertia circle. We've used the inertial circle method to turn link 3 into a three-force link, which is great because that means we can use our graphical methods to solve. Link 4 is, as before, simply a two-force link. It hasn't changed. And so we know that its line of action, just like in the previous two steps of this problem, is just a vertical line for reasons I mentioned previously. So it's vertical line like that. And this is our new K point up here, K3. It's the intersection of those lines of action, which you cannot see. There. Okay, so the only remaining line of action is the line of action of F23. That's the force that we're trying to find. We know that because this is a three-force link, all three lines of action have to pass through the same point. So we're going to sketch in that line of action. So just to be clear, this one is the line of action of the FIN plus the inertia circle, and this is the line of action of F23. Okay. So now we have our lines of action, and we have one force with a known magnitude and direction. We can sketch our force polygon. So again, I'm going to zoom out a little bit so we can see more of the page. So I like to start with our known force, F inertial. And I'm going to run out of room here again, so I'm just going to bring that down a little like this. We'll sketch in that line of action. The magnitude of that inertial force has not changed. So I'm going to use the same scale that I did for our previous force polygon. I'm going to do 5 centimeters. And it's up and to the right like that. This is our F inertial. That's 5 centimeters, which is 50 newtons. Or sorry, not newtons. My goodness, there I go again. Actually, I better make sure that on my previous notes, yeah, 50 pounds force. Okay. So that's 50 pounds of force. And I'm going to bring F4, 3 down. So again, we know that F4 on 3, the force of 4 on 3 is a vertical line. So I'm going to use my right angle triangle. To bring that down. Sketch in that line of action there. And then we have our other line of action, which is F2, 3. So I'm taking that line up here. Bringing that down. Okay, I'm going to run out of space again. Let me just turn this page a little bit here so I have more room. Okay, we're going to slide that line of action down here. My goodness, always running into things on the page. It's like that. Okay, that's our polygon. So all that's left is to draw the directions. So I'm going to zoom in for this part. Oh, nope, that's not the zoom. So we have our inertial forces in that direction. Sorry, was there a question or? No, okay. So this is the line of action of F4 on 3. This is the line of action of F2 on 3. So they're going to be head to tail, head to tail. So we get direction like that. This is our F2, 3. And we can measure it. And we get, look at that, 44 millimeters. So that's 4.4 centimeters or 44 pounds of force. So our final answer here is 44 pounds of force. And it's down and to the left. So, oops, don't know why I put that there. It should be here. 44 pounds of force down and to the left. Is that what we found previously with our superposition? Yes, it was. Actually, we have both answers here. We had 42 pounds of force to the left. So that means that our vector should be mostly pointing to the left, which we find it is. And then it should be pointing slightly downwards, 13 pounds of force down. And the vector sum gives us 44 pounds of force down and to the left. And that's what we found, 44 pounds of force down to the left. So that took me what? 10 minutes? And the other methods took us what? Like 30 or 40 minutes? So you can see that this inertial circle method is quite powerful. compared to using something like superposition to do your dynamic force analysis problems. So if you have any questions about that, feel free to come down and talk to me. I'll be here until the top of the hour because that's what I'm paid to do. So I'll be here for any questions. And I love it too. That's another thing. So I'm happy to answer any questions. Yeah, so I'll see you all next time.